Okay, so this will be the part B of chapters 2. This is a video that you need to watch. It'll be through the textbook. There's a component called Anatomy and Physiology Revealed. There's a list of these on the modules page. There's also a video to show you how to get to them. I embedded them in the PowerPoint, but for some reason, the last couple of years, they haven't worked. So I usually leave at this point, show the video from the Anatomy and Physiology Revealed, and then proceed. So this compares the ionic bonds with covalent bonds. We've defined ionic bonds, and now we'll look at covalent bonds. Covalent bonds are chemical bonds formed by sharing one or more pair of valence electrons. They're stronger than ionic bonds because with this type of bond, what we see is the electrons moving around, both nuclei. Yes, the valence shells have to touch. Down here, we see a single line between the two hydrogens in a structural formula. The one line represents one pair. Each of the two different atoms provide one electron to the pair. Continuing on that same line, if sharing one pair, we call it a single bond. If they share two pairs of electrons, we call it a double bond. These four are going to go around these two nuclei. Now, the other four that we see here, 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 and here are only going to stay around the oxygen nucleus. So yes, there are specific electrons that are part of the bond. If they share three pair, it's called a triple bond. So covalent bonds, they share electrons. They have to share pairs of electrons. If you cover up the carbon and just focus on this oxygen, there are 8 electrons going around in that second shell. If you focus on carbon, it has 8. This oxygen has 8. Okay, so Lewis dot for again, Lewis dot for covalent bonds. So with carbon dioxide, We're going to put carbon in the middle. It has 4 electrons. The oxygen, where we at? The oxygen has 2 electrons that it shares with the carbon, and you could put them closer. Let's see if I can get that. Two from the oxygen, and then it's going to have 6 or 4 more of its own. The other oxygen, same thing. What else shall we draw? The that would be carbon dioxide. Oops, CO2. If we drew something bigger, let's see, CH3OH, carbon with let's see, let's make the hydrogens black. So that one belongs to the carbon, hydrogen, hydrogen, hydrogen. Carbon's gonna have okay, my little, so carbon has a total of 4. So its 4th one will be over here. Oxygen will share 1 of its with that carbon. One, 2, 3, 4, 5, 6, and another hydrogen shares its bond over here. So Lewis dot. Covalent bonds. Okay, now, just like with children, some of them understand the concept of sharing and some of them don't. Non-polar covalent bonds. Non-polar covalent bonds are strong bonds between atoms that equally share valence electrons. So the electrons are going to spend the same amount of time around each of the 2 nuclei. That's because carbon has 6 protons and carbon has 6 protons. So they have the same amount of pull or affinity for those electrons. So it's equal sharing. An attribute of nonpolar covalent bonds and molecules, I guess, with nonpolar covalent bonds is that these tend to be hydrophobic. They don't want them to interact with or dissolve into water. So this is an attribute of nonpolar covalent bonded molecules. So think oils and waxes. We put wax on our cars and our skis to push away the water. Nonpolar, there's not a problem sharing, but it's not going to play with water. Polar covalent bonds are bonds that occur when electrons are shared unequally, producing slight electrical charges. So what happens is one of the atoms is going to get the electrons more than the other. Oxygen has 8 protons. Hydrogen has 1 proton. Make sure when you draw a polar covalent molecule that you include these slight charges. The slight symbol looks like the number 8. You just don't close the top. And then you put a plus or a negative next to it. You have to remember to put those 2 symbols or those kinds of symbols on water. Water will be the only polar covalent molecule that you have to draw. Again, water is the only polar covalent molecule. So whether you're drawing the atomic structure, the Lewis dot, or the structural formula, you have to put the slight charge on those. An attribute of polar covalent bonds is that these compounds are going to be hydrophilic. So they're going to easily react with water. They react with other polar molecules, which is water. They even react with ionic compounds. In a couple of slides, we'll see the difference between a full charge and a slight charge. So with polar covalent bonds, they have a problem sharing, but they play with water. 8 protons has a greater affinity than 1 proton. So think of tug of war. Oops. Okay, so now properties of water. You could take an entire class on water called limnology. The class, as it proceeds, will require us to review and use 3 of those properties, but there are several. So the first property is that water is an inorganic compound with polar covalent bonds. You can see this in the slight charges on the structural formula. Yes, all of that is the first property. Second property, water easily forms hydrogen bonds. So that part is the property. We need to define hydrogen bonds because we haven't done so yet. These are biologically a weak bond between a hydrogen already in a polar covalent bond and another polar covalent molecule. And so we see it as a dotted line rather than a solid line. Chemically, it's considered a strong bond because if we go back to honk, hydrogen's only supposed to be in one bond. Here, it's in two. So chemically, they consider it strong because it goes beyond the normal bonding potential. But in biology, we consider it weak because it's easily broken. Now, when you have thousands of them, they're quite strong. This is what holds DNA together. This is what helps hold proteins together. The third property is that hot water is a good solvent. When you have physical mixtures and you have an even distribution between solvent or solutes and solvent, that forms a solution. So here we see a solution of sodium chloride. You can see the sodium ion here in the middle, and it's the oxygen end that's attracted to it. But notice you have lots of water molecules surrounding the single sodium. So that's the difference between a full charge and slight charges. For chlorine, chloride, it's the hydrogen end of the water molecule that's attracted to the negative charge of the chlorine. Again, it's multiple water molecules to a single chloride molecule. So water's a good solvent. Couple of other properties that you won't get tested on, but you need to be aware of. Adhesion. Water has a tendency to cling to other substances, going back to making it a good solvent and the forming of those hydrogen bonds. Cohesion means that molecules tend to cling to each other. Then that's what we see here. The water molecules with those hydrogen bonds, it attaches to each other. Plants depend on cohesion. They create a water column in the plant, and if that water column is disrupted, then it can cause damage and the plant can die. When you get cut flowers, if you will recut the stems underwater about 2.5 inches above where the original cut was, you can typically reestablish the water column and the flowers will last longer. Water's thermal stability helps us to maintain internal body temperatures. With most substances, however much heat you add, that's how much the temperature goes up. Or however much heat it loses, the temperature goes down. Water's weird, it's different. You have to add heat before the temperature goes up. You have to add heat before the temperature goes up, which is why you see more stable temperature ranges in the rainforest and along the coasts of the oceans and other large bodies of water. So in the rainforest, like down in South America, they have a typical temperature range of 70 to 90. It doesn't typically vary much. Here, where we have way less water in the environment, we have a range of, -10 to 112. Another attribute of water, property of water, is that it's more dense as a liquid than a solid. Most things are more dense as a solid, and that's why ice floats. When a pond or lake freezes or river, it freezes from the top down. And that's how things can, fish and other organisms can live in a pond over the winter because it's the top that freezes, not the bottom. Okay, so now we have a place to draw, excuse me, the atomic structure of water and the two ions that are formed by water. Because water is weird. It can have the polar covalent bonds, or it can separate into two ions. So with water, you have hydrogen with its one proton or one electron. It's going to have a slight positive charge. Let's see if I can draw that bigger. Water with a single electron, it's going to have, or hydrogen, it's going to have a slight positive charge. Oxygen, it's going to share one electron there. It's going to have 5 more. 1, 2, 3, 4, 5, 6. And it has a slight negative charge. And the other hydrogen and its slight positive charge. So that would be water. Now it will separate into two ions. You have the hydrogen with its one electron. You have oxygen with its one electron there. And oops, 1, 2, that'll be 3, 4, 5, 6. And this whole thing is going to have a negative charge. Sorry. Okay, let's try this again. So, oxygen with 6 electrons. Hydrogen with 1. You have one electron there, so that makes this a negative charge. And then you have a hydrogen without any protons, and it has a plus charge. This is the hydrogen, ion, and this is the hydroxyl or hydroxide ion. Again, you'll need that for your chemistry assignment for two of them. Okay, so then you have a place for the ionization of water, which is what you see there, but in a different form. H2O will separate into a hydrogen ion and a hydroxyl ion. So and the reaction can actually go both ways. So in a body of water, in a glass of water, you're going to have water molecules. You're also going to have hydrogen and hydroxide ions. So ionization, this is the equation or reaction showing the ionization of water. That's one word. Okay, so mixtures. I kind of hinted at this when we did the properties of water. In a physical combination, there's no bonds, but you have things in the same place at the same time. So solutes are the substances in the smallest quantities within a mixture. Solutes are the substance in the largest quantities. Now, in our body, water is the most numerous solvent. It's not the only solvent, but it is the most numerous. One type of mixture, and you see all three types down there in those tubes. One type of mixture is called a solution. In a solution, which is this blue tube, you have a homogeneous mixture, meaning you have even distribution of solutes and solvents. Typically transparent, you can see the black lines through the blue fluid. The other tubes have heterogeneous mixtures, meaning that they're not evenly distributed. So this white one is what we call a colloid, where you have uneven distribution, but the solutes are small enough that they stay distributed. Typically cloudy, can't see through it, but it doesn't settle. These last two tubes have what we call a suspension. If we physically mix them, you see this even distribution. Over time, the heavy solutes will settle to the bottom and the lighter solvent will come up here. So this is why on some things, the directions say to shake it well. If you don't, and you take your material from up here, you're not getting any active ingredients. If you get it down here, you've got too much. So, yes, you got to follow directions. Insulin comes this way, you have to shake it up. The old calamine lotion, same kind of way. A lot of the antibiotics given to kids because they're liquids, same kind of thing. If you don't shake it up, you don't get the right amount of material. Overdosing or underdosing. Okay. pH. And yes, it has to be lowercase p, uppercase H, because uppercase H is the chemical symbol for hydrogen. It's the concentration of hydrogen ions in solution. Mathematically, it is the negative log of the concentration of hydrogen ions. These brackets in a mathematical equation refer to concentration. So it's a mathematically altered number. And we will discuss this in more depth when we get to chapter 24, where we talk about pH balance. So acids can be defined about 9 different ways. One of the ways is that it's a substance with large amounts of hydrogen ions. Another is that it can release hydrogen ions in solution. And a third, it has pH values of less than 7. Bases or alkaline are substances with few hydrogen ions. They will bind to hydrogen ions in solution, and they have pH values of more than 7. Buffers are weak acids and weak bases that regulate pH levels to prevent drastic changes. With pH, we only want small changes. You don't want to put 200-pound dad and a 50-pound toddler on the opposite ends of a teeter-totter. So think of the same things. What 2 toddlers or 2 kids same size on either side. So you just want little changes, not big ones. Okay, organic compounds versus inorganic compounds. Organic compounds typically contain carbon and hydrogen. They can have other elements, but those are the minimum. Carbon and hydrogen. And yes, you can use, the chemical symbols for carbon and hydrogen. That's acceptable. They usually, but not always, have covalent bonds because carbon needs 4 bonds and it typically shares. Usually, they're insoluble in water. Usually, and I didn't put that on the slide, but make sure you put usually in front of insoluble. They decompose easily. Mr. Raccoon that gets hit with a car tonight is not going to look the same in 2 weeks because he's going to fall apart. Examples of organic compounds include lipids, carbohydrates, proteins, and those are 3 groups that we'll look at with this chapter. Nucleic acids, like DNA and RNA, and vitamins are the 5 groups of organic compounds. Okay, inorganic compounds never mix carbon and hydrogen. They don't have a specific element that's present, but they never put those 2 together. Usually they have ionic bonds. However, we just covered a substance that is not, doesn't have the ionic bonds, but rather has polar covalent bonds, but it is inorganic, and that would be water. Usually soluble in water. Fall apart, separate. We use the term dissociate, go into solution. But these resist decomposition. The only reason Mount Rushmore is smaller than it used to be is because of the dynamite and chiseling that was done. So, sodium chloride, potassium chloride, sodium hydroxide, those kinds of things are inorganic compounds. Okay, functional groups. Functional groups are groups of atoms attached to a carbon backbone. They can determine organic properties of organic molecules. So you have 5 that you have to know, and you'll need the name, the molecular formula, and the structural formula. So molecular formula is OH for the hydroxyl group, which we also call the acid group, or the alcohol group. You'll have a line to the oxygen, and then you'll have a hydrogen. It's assumed that there's a line with the hydrogen, but because we see so many, this is a shorthand that's often used. If it's at the beginning of the molecule, then the hydrogen goes first and then the oxygen. So the line has to go to the oxygen, not the hydrogen. Going back to, oops, where am I at? Honc, HONC, 1, 2, 3, 4. Your second group is called methyl, and that's going to be CH3. Carbon is going to be surrounded by 3 oxygens. It doesn't matter which 3. And then the rest of the molecule would go out that way. If you put those 2 together, you can make methanol or methyl alcohol. Your third is amino, NH2. Nitrogen will have 3 bonds, and so 2 of them will be with hydrogen. Then you have carboxyl, which is COOH. It tells you there's a hydroxyl group. So carbon is going to be double bonded to the first oxygen, and then there's going to be an OH group. And yes, it could be linear. Now, carboxyl is an organic acid, so it can donate hydrogen ions in solution just like water did. So the ion, carboxyl ion, would be COO with a negative charge. It would lose the hydrogen proton, hydrogen nucleus, but it would keep the electron. So that's your last electrolyte that you need for your chemistry assignment in that one question. Okay. Your last one is your big one, and that's phosphate. Oops. In the biggest form, it's H2O. Oh. Can I even? It's HP04. So phosphorus is surrounded by the 4 oxygens. Two of them are going to have hydrogens on them. One of them is going to have a double bond, and then the one that's going to be attached to the rest of the molecules. Now, phosphate can also be seen as an ion, and it can be seen with less hydrogen. So HP04 is also phosphate. PO4 is phosphate. And then it can also be represented with a capital P and a subscript of a lowercase I, which is inorganic phosphate. So you'll see that various places, but phosphorus is always surrounded by the 4 oxygens. And don't try and make it make sense with which column phosphorus is in, because it's weird. So functional groups. Your functional groups need to go on part of that small periodic table. So that's something that you need to do. So you have those with you on your periodic table. All right, so that marks the end of section B for chapter 2. Oh, for